My name is Nidhi Sharma, and I'm currently working as an assistant professor in Computer Science and Engineering Department at Satyug Darshan Institute of Engineering and Technology. Today, I will deliver a lecture on the topic BFS and DFS, that is breadth first search and depth first search. So let's start. So first of all, we should know what is BFS. BFS stands for breadth first search. Basically, it is a vertex-based technique which is used to find the shortest path in a given graph, right? It uses data structure called Q, and Q follows, as we already know, that Q follows first in, first out, right? In BFS, first vertex is being selected at a time, and then it will be visited and marked, then its adjacent are visited and then stored in a queue, right? So we have an example. First of all, suppose I have marked A, right? My root node is A. So I have marked A as being visited, right? Then we will go for its adjacent vertices. Now adjacent vertices of vertex A is B and C, right? Then we will go for B and C. We have an option. Either we can choose first B or we can choose first C, right? Now in this output, I am choosing B as first. So first A has been visited, right? We will print it. Then B is being visited, right? Then adjacent vertex of A is C. So C will also be visited. Then it will print. Then first of all, B's adjacent vertices is D. So we will visit it D and print it. And then adjacent vertices of C is E and F. So we will print E and F. So the basic thing of, or we can say the first of the technique of BFS is we will first select the vertex, mark it as a visited node, and then we will go for its adjacent nodes and then do the same for that adjacent nodes. Clear? So now we'll go for another example. Suppose I have given this graph, right? We have 6 vertices. We have an array which stores 6 digits, right? 6 numbers, and then we have a queue, and we have also an array of output, right? We have also an array for output. We'll see later on. Then first of all, visited is being, by default, all the values of visited array is 0, right? So that means none of the node has been visited yet, right? The first step will be, we will visit first node, right? The first node is vertex 1. So we will visit it 1. As you can see that the blue color represents that the node is not being visited yet, and orange represents the node has been visited, right? So first of all, 1 is being visited. So the color is changed to orange. Then in the array of visited, we will mark it 1. We will overwrite 0 with 1. That means 1 is being visited and the rest 1 are unvisited right now. Now we will put that 1 in a queue, right? So we have put this 1 in a queue, and as we know, it follows first in, first out, right? Now, then we will print that 1 in the output queue, right? Now we will print that 1 in a output, right? Then after printing, you can see after removing 1 from queue and printing it, we will enqueue its non-visited adjacent nodes. So we will, what we will do now, after we have print 1, so we will enqueue its non-visited adjacent nodes. Now its non-visited adjacent nodes of 1 is 2 and 3. So I can take 2, or I can take 3. Now in this example, I have taken 2 first. Then we will see, we will mark 2 and 3 as in that these nodes are visited. So we'll mark 2 and 3 as 1. You can see here that 2 is being marked 1 and 3 is also being marked 1. That means 2 and 3 are now visited and the color is changed to orange, right? Now Q. Now we will enter, you can say we will add these 2 and 3 in Q, right? Now again the same step. Now 2 will be removed. In the queue, we will enter the elements at the end, and we will remove the elements from the front. So we will remove the element 2 because 2 is in the front of the queue. So 2 is being removed from the queue, and then it will print in the output. You can see here, see 2 is being removed from the queue and it is print in the output, right? Now, when 2 is being removed, now we will move on its non-visited adjacent nodes. Now, 2 non-visited adjacent nodes are 4 and 5. So, the color will be changed of 4 and 5, right? You can see. Now, 4 and 5 is also being marked as 1 in the visited array. 1 means it has been visited now, right? And it will also add in queue also, and we will add it in the end. So 4 will be added, then 5 will be added. There can be a possibility that you can add 5 first and then 4. It's all up to you, right? Then what we will do, the same thing we will do, that I will remove 3 from the queue, and then I will put it into the print. Clear? I will put it into the 3. Then we have remained 4 and 5, right? Here you can see I have only 4 and 5 in the queue. Now, adjacent nodes, non-visited adjacent nodes of 3. Now you can see adjacent nodes of 3 is 5, right? But you can see that 5 is being already visited. You can see here, or you can see the previous step, that 5 is being visited, right? So we will remove 4 from the queue, and then we will print the 4, right, in the output. Clear? Now, see here 4 is being printed. Now we have 5 in the queue. Now 4 adjacent nodes of 4 is being searched. So adjacent nodes of 4 is 6 and 5. And now you can see that 5 is already being visited, right? Now 6 will be visited and marked it as 1, and I will add it in the queue. You can see here that 6 is being marked 1. The color is being changed, right? And then 5 and 6 will be in the queue. Now what will I do? I will remove 5 from the queue and I will print it. Then I will again search for the 6. Right? Then I will search for the 5, that any adjacent node of 5 is being unvisited. I can say that adjacent node of 5 is 6, or you can say 4, or you can say 2, or you can say 3. But all of them are visited. You can see here that all of them are being visited, right? So what we will do? We will remove 6 from the queue and we will print at the output. So my output of this graph is for BFS 1, 2, 3, 4, 5, 6. You have more than one output for any given graph of BFS. Clear? Because if I'm choosing here 1, then 2, you can choose 1, then 3. So there may be a possibility of more than one solution. Clear? So this is my BFS. Now starts for DFS. DFS stands for depth first search. It is an edge-based technique. BFS is a vertex-based technique. It is an edge-based technique. It uses data structure called stack, and BFS use data structure called queue, right? Then what it will do? It will first visit vertices, then are pushed into the stack, right? First we will visit the vertex and pushed into the stack, and second, if there is no vertices, then visited vertices are popped out, right? So stack is pushed in and popped out. Clear? So this is my example of stack. First of all, A is being visited, right? I have chosen A. Then A is being put it in the stack. Then I will put B into that stack. The names define that it is depth first. That means we will go into the depth, and that is breadth first. We will go into the breadth, right? So in this, we will go into the depth. So first of all, A is being visited, right? Then B will be visited, then D will be visited, right? Then we'll come back, right? And then we'll come to see that if there is a node, it's just a node of B, no. Then we'll come back to A. Then I will see if there is an adjacent unvisited vertex of A. Yes, it is unvisited, which is C. So we'll come to C. Then we'll come to E, either E or F, right? So my DFS for this graph is A, B, D, C, E, and F. Clear? You can have more than one DFS for a given graph, like BFS. Clear? So we'll discuss with some more example. This is my graph, right? So first of all, I will use the data structure called stack. Stack means push in and pop out, right? Then first of all, blue is defined as an unvisited node and orange is defined as a visited node. Clear? So first of all, A is being visited, right? So I will push A into the stack. You can see it. A is being visited, it is being marked orange, and now A is being pushed into the stack. Clear? Now it is depth first, so I will see the adjacent nodes of A. Adjacent unvisited nodes of A and A is B and C. Either I can choose B or I can choose C. So in this example, I have chosen B. Okay. So B will be pushed into the stack. Here you can see that A and B is being pushed into the stack. Okay. Now adjacent nodes of B unvisited is D, or I can say E. So I can choose any one, D and E. So I am choosing here D. So D is being pushed into the stack, right? Then I have option, either I can choose E or I can choose F. So adjacent nodes of D is E and F. So here I'm choosing E. So I'm pushing E into the stack. Clear? Now we will now E is being pushed. Now E's adjacent nodes is F, D, B, and C. Right? So I can take any one of them, but I know that B and D is being visited. Right? Now F and C is being remain. So I can select either F or C. Right? So F is being selected. So first of all, if F is being selected, so F will be pushed into the stack. Clear? So my output is here. I have pushed A, B, then D, then E, then F. Clear? Now F is being, so now we will see F. F adjacent nodes are what? D and E. And I can see that D and E are already being visited. But I have 6 vertices, but in the stack I have only 5 vertices. So one vertex is remaining to visit, right? So what we will do, we will pop out F. What we will do, we will pop out F. हम F को क्या करेंगे, निकाल देंगे. तो F is being popped out. Now we'll come to E, right? Now you can see that adjacent nodes of E will be B, D, F, and C. Okay, so as I said that F is being removed from the stack. Now adjacent nodes of E is B, D, F, and C. So B, D, F, I can see that they all are visited, right? Now only C is remain. So C will be pushed into the stack. So my output will be A, B, D, E, F, and C. Clear hai sabko? Clear? So this is what my DFS is. And I am repeating it again that there may be a possibility that one or more than one DFS can be formed from a given graph, right? So this is, and at the last we will pop out C, E, D, B, and A are one by one will be removed from the sense stack. Since all nodes are visited, no more nodes are being added and the stack will remain empty. Clear? So this will be the output of my DFS. Clear hai? everyone? Now, as we have studied BFS and DFS, now we'll discuss about the difference between the BFS and DFS. As we have studied, BFS stands for breadth first search. DFS stands for depth first search. We can also mention that BFS is using vertex based technique and DFS is used for edge based technique, right? It is also a difference. BFS use what data structure? It uses queue, and DFS use what? Stack data structure, right? BFS can be used to find single source shortest path in an unweighted graph. What it will be used? It is used to find a single source shortest path in unweighted graph, because DFS will we reach a vertex with minimum number of edges from a source vertex, right? That's why we are using BFS as a shortest path in an unweighted graph. But in DFS, we might travel more edges to reach a destination from a source, right? Third point is BFS is more suitable for searching vertices which are closer to the given source, right? BFS is suitable for the solution which are closer to the source, but DFS is suitable for the solutions which are away from the source, right? You can easily relate that BFS is breadth. Breadth means, first of all, it will search horizontally, and what DFS means depth. It will search depth vertically. Clear? Now, BFS considers all the neighbors first and therefore not suitable for decision making trees used in games or puzzles. So it is a drawback of BFS that it will not be used for games and puzzles, right? But DFS is used, it's more suitable for games or puzzle problems. Why so? Because when we make a decision, then we will explore all the paths through this decision. And if this decision leads to win situation, we will stop. So what we do in, so that's why we are using DFS in games or puzzles. And the last point is the time complexity of BFS is OV plus E, and DFS also we have the complexity O B V plus E, where V stands for vertices and E stands for edges, and the time complexity is O B V plus E. Thank you for your attention. Thank you so much.